Non-standard analysis is to standard analysis what non-Euclidean geometry is to Euclidean geometry, but non-standard analysis is more useful. Imagine a mathematical world in which every sequence, every series, every integral and every function converges to a unique evaluation. A world in which even 1 over 0 has a unique answer. Infinities cancel. Infinity times 0 equals 0. Pure fluctuations are rejected at infinity, and infinite sums converge. Before we begin, practitioners of non-standard analysis use the symbol omega for infinity. Non-Archimedean on an ordered set just means that infinite or infinitesimal numbers must exist. Infinite numbers behave just like real numbers. Infinities cancel. Multiplying by 0 generates 0. N star is the set of hypernatural numbers. I can't rearrange the terms in a series and expect to get the same answer. The standard part function removes infinities and infinitesimals. 1 plus 2 plus 3 plus 4 plus 5 is just the triangular numbers. The third and fourth rows were found by Wolf. The fifth row was found by Grandy in the year 1703. Decimal notation doesn't suffice for infinitesimals. Save this table for later. All I've done here is set pure fluctuations to 0 at infinity, keeping in mind that 0 times infinity equals 0. The Dirac delta function first appeared in the years 1822 and 1827. It was popularised by Dirac in the 1940s. The log of -1 is plus or minus I pi plus an arbitrary number of 2 pi i's. 1 on 0 is the log of -1 times the delta function. H is the Heaviside step function. Gamma is the gamma function. When alpha is an integer, e to the I pi alpha is just plus or minus 1. Finding logarithm of 0 is done the same way. For the renormalization of gravity, one solution is to set the ultraviolet cutoff to infinity. Infinity divided by infinity equals 1. Evaluate each Feynman integral as a sum of an infinite and a real component. Robinson's standard part function is used to recover the real part of each Feynman integral. Add them together as a series. The series converges on the hyperreals. This one is straightforward. This is just standard complex analysis. The absolute value of tan is a nasty elementary function. At the infinite limit, it behaves like the log of infinity. Numerical approximations are useful for all those problems where analytic solutions don't exist. The ratio of the number of real numbers to the number of rational numbers is approximately pi squared times 2 to the power infinity over 3 infinity squared. The differential of the Weierstrass function is exactly 0 for all values of x that aren't rational numbers. In non-standard analysis, I see no reason why this function can't be differentiated to all orders. Hilbert's third problem is called scissors congruence. It's the proof that it isn't possible to cut a tetrahedron into a finite number of pieces that can be reassembled to make a cube. The use of this function comes from the mathematician Hadwiger. It's easier to define the hyperreals than the reals. The top left of this table is the Hahn series. The top right is binary or decimal notation. The bottom left is Conway's surreal numbers. The bottom right is the Dedekind cut. The standard part function is to non-standard analysis what the real part function is to complex analysis. It is applied at the end of the calculation. I haven't found any counterexamples to the following proposition. The limit of every sequence has a unique evaluation. Pure mathematics went wrong in several stages. Initially, there was a quasi-religious belief in the infallibility of decimal notation. Leibniz and Euler got it right. Leibniz in the year 1703 and Euler in the years 1748 and 1755. Cauchy came much later, in 1821. Final look. I have other YouTube videos on non-standard analysis. The main one is titled Which Infinity? Parts 1 to 8, just the slides. Thank you.